mentioned in the contribution from Jim Gray, we mentioned the ACID is properties for transaction, right? And this ACID is short for the atomicity, as well as consistency, isolation, and the durability. In this page, when we talk about atomicity, the formula all the transactions in our database system must be atomic. In other words, their effect should be either all or none. And the database system must be consistent before and after the transaction executes, and not necessarily during the transaction execution time. During the time we may have some inconsistent states is fine, however before and after the transactions, we have to maintain the consistent states for our database systems. In other words, to maintain these properties for the transactions, we can either a transaction must be executed fully and commits. In other words, it commits all the changes it makes to the database system. All the transactions can be either sorted as never executed at all. In other words, we have to roll back. Right. In this way, we can maintain this consistent state for the transactions before and after the running time. So this properties is very important. And based on this property, we can design a strategy to maintain or to handle this crash recovery in the following pages. Besides this atomicity, another property we need to talk about is consistency. The transaction takes the resources from one consistent state to another. And each transaction must leave the database in a consistent state if the database system is consistent when the transaction begins. In other words, if we run a transaction before the running time, the database system is consistent. Then after we finish this transaction, we also need to ensure the database system should also be consistent. It is important. In this way, we can maintain the security of our data in the database system. Also, besides consistency, we also need to maintain its isolations. In other words, the transaction's effect is not visible to other transactions until this transaction is committed. If we make some changes to my post in Facebook, after I finish uploading the videos or posts, and then you can see my uploadings, right, or updates. However, before or during the committing time or uploading process, you will never see my uploading the videos or photos, right? It's called isolation. If I do something there, you can see it after I finish it. And my uploading process is not interactive with yours. If I make a mistake during the uploading process into Facebook, you will never be affected, right? Another property is called durability. Changes made by the committed transaction are permanent and must be surviving in the system from the crash recoveries. In other words, if a transaction is committed, it means it runs successfully. And later on, if the system crashes, we need to make sure all these committed transactions are executed and we get the results after these transactions. We cannot do this rollback before this committed transaction, right? If I do a transaction there, it is finished successfully, and later on, if the system crashes, changes made by my transactions must be executed again. This is very important. And based on this ACID, these properties, we can design a strategy to handle the crash recoveries. So based on these 4 properties, we can design a strategy we can use to handle the database systems from the crash recoveries. Actually, in the real world, the system will be more complicated. This complication can come from different scenarios of different sources. It can come from the database system may have multiple simultaneous users. And for some systems, the users' number can be very huge, the millions of users using it at the same time. So the simultaneous users implies multiple simultaneous transactions, or it implies multiple simultaneous database access. We will have multiple programming and multiple processes running at the same time in our database system. We need to ensure the system is secure and consistent to handle this kind of large amount of simultaneous access. And all the things can go wrong, right? Some transactions may conflict with one another. Even though we mentioned we need to maintain these isolations, however, if we have multiple transactions running on the same account of your banking account, right, If your parents and you are working on the same bank account at the same time via cell phones, in other words, this transaction will conflict with each other actually. We would handle them properly. Also, the programs may also crash. If it is a computer, it may crash, right? The program may crash, the operating system may also crash. If you are running your own Windows, you know that these Windows may crash very often, right? Also, the disk may also crash. All the hardware we are running may crash as well, right? If the system crashes and we loss of data, then the company will suffer a lot from this problem, right? The system may lose customers, get sued, and even goes bankrupt. It will be a very big problem nowadays. However, even though we have these so many different complicated problems, we still make sure the database system can never go wrong. If a database system data is 1% inaccurate, then the system is 100% unusable. We don't expect the system can go wrong. Also, the database system can never lose data. If we store data there and after crashes, the data is lost, it will be a big problem, right? And also, we also need to make sure the system can never become unavailable. We have to access it, and this system should be running, should be available all the time. You can see we have very strict requirements for a database system. And to meet these expectations, we have to design lots of strategies very carefully. That's the reason why the database system is so complicated, so hard to do in the real world. Okay, so this is about these complications in the real world running time for database systems. Now, in the following pages, we will go to the transaction handling for the crash recovery.